Now, even the single slit diffraction demonstration for the Heisenberg uncertainty principle, one could raise objections to. So we're going to try a very quick third example that I think will help remove some of those possible objections. So a possible objection to the slit experiment would be that, well, maybe it has something to do with the slit. The slit. It's the slit's properties, not the properties of these electrons we were sending through, but maybe it's the slit's properties that result in this spread in the momenta. So what I want to do is to make a new experiment, a new slitless experiment, but it's going to be slitless diffraction experiment. Now, because it's still going to be a single slit diffraction experiment, the analysis of the momenta and so forth would be very similar. But it's more really the experimental apparatus here that I think really underscores the fact that we are dealing with something truly fundamental about our particles. So here's how this experiment will go. Once again, I will have my source. And it's emitting electrons off in all kinds of different random directions. They all have the same energy, E equals p squared over 2m, although technically I should call that h. And I'm going to make sure my source is very far off here to the left. Now, the trick is how I'm going to design this single slit. So here's my single slit apparatus. But now I want you to really think in 3 dimensions, because I'm not going to make like a wall, but I need to emphasize the 3rd dimension. So just imagine this plane here, like so. So I've got like a planar slit, and these sides, of course, are extending, as far as you like in these other 2 directions, in and out of the board. Now, why I'm emphasizing the in and out of the board dimension is the way I'm going to affect this slit, or how I'm going to create this slit. There's not going to be anything that's really in the path of the electrons at all, but deep down below the page, I'm going to put a series of very strong gamma ray emitters. And they're going to send gamma rays horizontally across, and I'm going to have some gamma ray detectors on the other side. So these are gamma detectors. So basically what I'm creating here is an electric eye, right? Like the same kind of thing you have for your garage door opener at home. And if something breaks that beam, you will know immediately. So I'm going to have a whole series of these emitters on this side that are sending, again, their gamma rays across, and I've got detectors over here making sure that they will tell us immediately if we see any electrons coming through. So here's all my detectors down this row, and here's all my emitters. The emitters are far down below the plane. The detectors are far above the plane, so the electrons can just sail right on through. They might cut my beam, or they might go straight through, but they can certainly travel along however they like. So I'm just putting some more of my gamma rays in here. You guys get the idea. Okay, now, the real question is, okay, what am I going to detect on my photoplate? And the result is actually really fascinating. It's going to look something like this. So I'm going to draw here on this axis, of course, the brightness. This axis is the x-axis, as we had said, but on this axis, I'm going to show you the brightness for each point x. And what you notice is there is actually a peak in the center, right? But the peak doesn't go down to 0. It hits a certain minimum value, and then it bounces up, and then it just kind of approaches that minimum value as I get far away. And the question is really, well, what accounts for that type of a result? Now, and this is really true. If you really did this measurement, this is exactly what you would see. These guys are all writing on some background. Now, the result is as follows. The nice thing is the experiment can tell us, though, what distributions we get if the electron broke my beam or if it didn't break my beam, right? I can set up electronics to count things separately. And here's then the result of the experiment. So the question is, how do I get this pattern? And it turns out that pattern is equal to the sum, right, of two different patterns. One that I get for electrons that break the beam, right? They break my beams, right? That means they were detected as not in the slit. And the other, I'm going to make this look a little more straight like my photo plate. So it's the sum of these two contributions is what I had drawn up above. And the other one is that electrons that, and this is key, touch nothing. Right? Nothing touched these electrons. Right? They just sailed through. Any electron that hit a gamma ray, we will detect that event. So when the electron breaks the beams, right, so they're detected as being not in the slit, right, they went through one of these other pathways. When they hit those gamma rays will scatter them in all different directions. And so what they do is they end up producing this kind of even background on the plate. You get basically a constant value from them. Right, this is the x-axis again. This is going to be my x-axis. This axis is my brightness. And same thing here. This axis is my brightness. But now for the electrons that nothing touched, right? So this is why I'm saying this is an inherent property of these electrons, because I'm just looking at electrons. No one's interfered with them. The only thing I've done with these electrons is to make sure that I know they arrive in this range of x values as they immediately pass through my slit. And what they do is to produce exactly your standard single slit interference pattern. So that's how we know that this diffraction pattern, with its momentum limitation, it's exactly the same diffraction pattern. The momentum spread is 4, right? It's the momentum spread of if you want, I'll make up a word, interfered with, non-interfered with electrons. They still produce that same momentum spread. So I hope this will help you to see that, in fact, these properties that we've been exploring are inherent in the particles themselves. Nothing really to do with the probes that are involved. Nothing to do with the particular details of the experiment. It's just how those electrons seem to move through space. The other thing that I'm hoping you will see is the precise meaning of the terms in the formal Heisenberg uncertainty principle. Just like we did here, the key is you first do some kind of a measurement, like passing particles through a slit, and then the particular spreads that we are dealing with are what immediate follow-up measurements of position and momentum would give you, because those tell you really how well you had determined the state of the particle before those measurements. And with that, then, we will be, on this note, concluding today's lecture.